Welcome to class. Been a while, feels like it's been a long time since we've seen each other, a whole week. So hope you guys are doing well. Hope you enjoyed your long weekends, enjoying the unusually cold weather in Denver this time of year. So the plan for today is to take a look at some more applications of first order differential equations. In particular, we'll be looking at heating and cooling problems today. And then next week, we are going to start material in the next chapter that is dealing with second order differential equations. So we'll move on to second order differential equations next week. Today is kind of like a wrap on first order differential equations and applications of those. So before we get started, I just want to let you know that there's no homework due next on Monday because we've only really had one class. So the next homework assignment is due in a week and a half. So it's a little bit longer because it has some extra days in there. So just be sure you're aware that it might be a little bit longer. Don't wait until 2 weeks to do it. Definitely get going on it sooner rather than later. But any questions before we get started today? Okay, so to get started, I just want to think about this problem over here. This is a pretty typical Calc 1 problem that you might encounter when you're first thinking about derivatives. So derivatives are not all of these shortcuts for formulas that we learn, right? But derivatives are a measurement for a rate of change. So when we don't have formulas, knowing all of these shortcuts don't really help. But the idea is this notation f prime, we calculate this, should say by writing this as say like dy dx. And oftentimes, if we just have a couple of data points, then we can approximate the derivative by looking at the slope, right? The change in x over the change in y. So if I'm trying to approximate the derivative, say, of this function f at x equals 6, what could we do to get an estimate, an approximation for that rate of change? So feel free to chat it in or take the mic if you've got a suggestion about how we can estimate these derivatives from a table.
Would it just be x to n minus 1? So minus its previous?
This is not a power function. We don't have a formula here. So we can't use any of these shortcuts like bring the power down and subtract by 1. We just want to use definition of derivative, which says it's a rate of change. And so most of the time in life, we actually don't have formulas for things. So all of these shortcuts that we learn in calculus are not helpful when we're dealing with data sets with real data that doesn't have a formula that it's matching. So if I just have a collection of data points like this, and I want to approximate the slope at time 6, all I can use is the data points that I have here. And what would be one way that I could use this data to estimate the slope of the function at 6?
Just take 2 data points, like 2 ordered pairs, and then just calculate the slope.
Okay, so like which 2 points would make sense to use if we want to do the derivative at 6?
So what you'd have to do is you'd have to use 6 and 6, 15, 9, 16.
Okay, so one thing we could do is take these 2 points over here, and the picture here that you might have in mind is we have a bunch of points like this, and we don't have a curve that goes through them. And so here we are maybe at time 6, and we're trying to approximate what is the slope over there. So what I can do is pick 2 points, calculate the slope between those 2 points, and that will give me some estimate for what the slope is at the instant x is equal to 6. So one way I could do this would be look at the change in y between those 2 points. So that's the 16 minus 15, and then divide that by the change in x. That's exactly what we're using from this formula over here. So one way to estimate this might be that the derivative is approximately what's happening is y is going up by 1 when x went up by about 3. Any questions?
Could we use the 3-6 data point too, or would
Yeah.
that 3
So,
1?
so this would be what we would call like a right-hand estimate for this.
Okay.
But if you think about like if this were our position and we were wanting to measure our velocity, you would want to take into account how fast were you moving just after 6 and how fast were you moving just prior to 6. That's right. So you also might want to take into account what's happening between these 2 points. And for that calculation there, you would have like 15 minus 12. And the change in x is 3 again. So this one would come out to be approximately 1. So I know that just prior to x equals 6, the slope is about 1. Just after x equals 6, the slope is about 1/3. So using both of these bits of information, we can say that the derivative at 6 is going to be somewhere between 1 and 1/3. And we typically pick like the midpoint between those two, which would be 2/3 here. So if we were asked to give like the best possible approximation based on this table, then this would be the best estimate because this takes into account both what happens after 6 and what happened before 6.
Can I ask a question?
Sure.
Since at f of 3 to like 6, it was 1, and then from 6 to 9, from 6 to 9, it was 1/3.
Mhm.
Would we claim that the derivative was a negative slope since it went down?
So the derivative is decreasing, so that might tell us something about the second derivative. Yeah, but the first derivative is positive because the function is always increasing.
Okay.
Yeah, so the derivative, when you're looking at how is the derivative changing, then you're actually thinking about the second derivative. Yeah. Okay, any other questions? Yeah, and so oftentimes this is like where you start derivatives and then you learn these fancy formulas about shortcuts and then you forget about this stuff and actually this is the stuff that's more useful than those shortcuts in the long run. So I want to definitely be sure we're able to do some numerical approximations. And let me just say that you can get this estimate by doing 2 separate calculations like we just did. Or this would be equivalent to saying, let's take this point over here, this point over here, and just calculate the slope between the points just prior and just after x equals 6. So I could have approximated this by looking at the change in y and you would get that that is actually 2/3. That should be equivalent to the 2 separate calculations that we just did. And for other points, such as if I wanted to calculate the derivative at 0, we don't know any information about what the value of f was prior to x equals 0. So in this case, the best that we could do would be to pick these 2 points and come up with an estimate by taking the 12 minus the 3. So that would give us 9 divided by 3. So for the endpoints at x equals 0, I only know 1 point to the right. And for the same reason, if I wanted to estimate the derivative at 12, all I could use would be the 1 point prior to time, or x equals 12. Okay, any questions? So a lot of this stuff, a lot of differential equations is really just it's like Calc 4. We're just going to apply lots of these results from calculus. So the situation I want to think about today are the rate at which things heat or cooling. And we can take a look later in class at some applications of this, both in terms of economics and supply and demand curves, as well as to forensic science and trying to find the time of death for somebody. So let's first just think about, and really what we're thinking about is the rate at which these things are cooling. So let's just imagine you've got a coffee cup that you set down on a table in a room. So what we are measuring in this table is the temperature of the coffee, say T minutes after you've placed it in the room. So initially it is 160 some odd degrees Fahrenheit, and 14 minutes later we can see it's about 71.5 degrees Fahrenheit. So over here is T, over here is C, and what this is asking you to do is estimate the derivative at each of these times. So you can use the idea that we just used on the previous slide or on the previous page. So for example, if I want to calculate dc dt at say time t equals 2, so if I wanted to calculate the derivative at that time, then we could take this same approach that we just did, which is say, we could take a look at a point just after it, calculate the slope between those 2 points. We could take a look at a point before it, calculate the slope between those 2 points, and then average those two together, which again is the same as saying, let's take the temperature after time 2. Let's take a reading of the temperature prior to time 2, which would be at time 0. So let's look at the change of temperature over some interval of time, both before and after time 2. And then we're going to divide that by the total change in time over this interval, which is a 4-minute interval. And then calculating this comes out to about minus 15.55 degrees Fahrenheit per minute. So that is telling us that 2 minutes after you've put this cup in the room, its temperature is decreasing by about 15 degrees each minute. Any questions where I got that value from?
Just because it's not stated, we wouldn't be able to find the original derivative at time 0, correct?
So we could, yeah. So if we wanted to, we just might have to do it a little bit differently. But if we wanted to calculate the derivative at time 0, in this case, we don't have any information about the temperature before time 0. So all we could do is take into account what happens after time 0. So in that case, we would approximate this by taking the temperature at time 2, subtracting the temperature at time 0. We're still doing change in C over change in T. We just have a little bit less information, so we only have one additional data point in that case. So that would come out to be like 160.3 minus 120.4 all over. Now the change in time is 2. So I think that's close to minus 20. And you would have kind of like a similar issue. at the last point where here you would only be able to compare what happened over the interval from 12 to 14 minutes.
On that second one that you did for using points at 0 minutes and 2,
Mhm.
isn't that reversed on in the numerator? Shouldn't it be?
Yeah, thank you. You're right.
Okay, cool. Thanks.
Yep. Yes, it should be C of 2 minus C of 0. Yep, thanks. Okay, any other questions about these calculations? So the others follow similarly. If you don't have any questions, I'll just fill them in. But these calculations are coming from exactly the same way that we did the derivative at 2. So these are coming from taking data, what happens after that and prior to that, and then averaging those rates of change. So these are the values that I was getting repeating this sort of calculation. And so one thing that we can see is the rate at which the coffee is cooling is slowing down, right? At first, we can see every minute that goes by, the temperature is dropping a lot, and then eventually this drop is kind of flattening out. So ultimately, what we'd like to do is find the model for this coffee with respect to time. And we're going to do that by first figuring out a model for how the rate of change of the coffee depends on C and T, possibly. So down at the bottom, it's saying, well, let's try and come up with a sketch. We're not trying to sketch the solution. What we're sketching here is how does the derivative dc dt depend on these two variables in our model, which would be time and the temperature of the cup of coffee. So what I'd like you guys to think about is this question here. We're going to find an equation for dc dt. And what we'd like to think about, similar to how we thought about population models, what things are going to have a role on the rate of change of the coffee? Is it going to depend on the temperature of the coffee? Is it going to depend on time? Or is it going to depend on some combination of those? So a couple things to consider when we're trying to answer question number 2. So if you want to think about, well, does this depend on time? Then what you can think about are if 2 cups of coffee have the same temperature, but at different times, would their rate of change, would the rate that the coffee is cooling be different for those 2 cups of coffee? So for example, if I have a cup of coffee and at first it's 160 degrees, 6 minutes later, it's 85 degrees. Somebody else comes into the room, they have a cup which starts off at 85 degrees Fahrenheit. Like, how would you think those 2 cups are cooling? Okay, and so in this case, those 2 cups have the same value for C. They're both 85 degrees Fahrenheit, but different T's. Right, one of them is 85 degrees at time 0. The other one is 85 degrees at time 6. And then let's think, okay, would these 2 cups of coffee be cooling at the same rate or at different rates? And that might help us identify whether this thing depends on time or C or not. And in red over here, what we've got are these 2 cups of coffee have the same T value. So we're placing them in the room at the same time. But at this time 0, they're going to have different C values. So these 2 cups of coffee are different temperatures. So just a really quick poll that I want to take be to get your thoughts, and I'm not asking for big detailed analysis here, just what does your gut tell you about the rate of change of coffee? Do you think it's going to depend on the temperature of the coffee? Do you think it's going to depend on how long it's been since the coffee has been sitting in the room? Okay, take another 10 seconds, please, for those that are still thinking about it. Okay, so here were the results. And so people were a little more uniform about their thinking for the first one as opposed to the second one, which you can see pretty uniformly distributed in your responses there. So for the first one, those that said it is going to depend on C, that is true. And so if we think about this scenario over here, kind of what's going on in the red scenario, and that is if we take 2 cups of coffee, we place them in the room, one of them is 160 degrees, the other one is 90 degrees. The cup that's 160 degrees is going to cool faster than the cup that's 90 degrees. Okay, and if you think about taking this to the extreme, if you took a cup of coffee that was exactly the same temperature as the room, then the coffee wouldn't change at all, right? It would just stay the same temperature. So the more our coffee differs from the ambient temperature of the room, the faster the coffee cools down. Okay, so if you think about that, like a 200-degree cup of coffee is going to cool a lot faster than a 75-degree cup of coffee. So the temperature of the coffee definitely has an effect. And so I think most people were thinking about that. As far as if it's going to depend on time, if we think about the situation in blue, it doesn't really matter what the time is as far as how fast this thing is going to cool. If I take a cup of coffee, put it in the room at time 0 and it's 160 degrees, and wait 6 minutes and it's 85 degrees Fahrenheit, that cup of coffee is going to cool at exactly the same rate as a cup of coffee that began at time 0 with 85 degrees Fahrenheit. So it's not necessarily how long has the coffee been sitting in the room that makes a difference. It's mainly what is the temperature of the coffee. That's going to determine how fast it's cooling off. So this is going to be a function of only C. So our differential equation is not going to depend on T at all. Any questions? Okay, so I want to come up with this little plot using this app. So if you want to open up this applet, go for it. If you don't, I'll share my screen. I've got it open on my computer. And so the website looks like this. And first thing it's doing is it's just asking us to enter in these values that we calculated. So I'm going to enter in the values that we had on the previous page. And what's going on in the graph, it's saying, okay, if the temperature was 98.1 degrees, this dot over here is saying at a temperature of 98.1, we can see the rate of change of the coffee is about like -9 degrees Fahrenheit per minute. And the goal here is we want to take a look at this data and then come up with a model for how is the rate of change dc dt depending on the temperature of the coffee C. So here's kind of what the data would look like if we plotted it. And I'm going to get rid of this last one that we had over here and this first one that we had over here, since these were calculated just a little bit differently than all of the ones in the middle. And so if we're trying to look at this relationship, anybody have a guess about what might be the relationship between C and dc dt? Like what pattern do you think you might see in these blue dots?
It's linear.
Yeah, it looks like it might be linear. They seem to be lining up pretty close in a line. So let's try and fit a curve to that. I hit the curve fitting option. I think it takes a second to work. There it is. Okay. So now what we're going to try and do is fit a curve so that we can come up with a model of how does dc dt depend on just the temperature C. And my curve here, what I'm going to try and do is fiddle around with this so that it most closely matches the points. It seems to have about the right slope. We want to increase this a little bit. Okay, and then we can kind of play around with the slope a little bit more if we wanted to, but this seems to be pretty good estimate for our model here. And so what this is telling me, so you guys can see this little formula that I'm moving around, right? Yeah, so this is telling us exactly what is the formula for this line. The line has approximately a slope of minus 0.3, and it has an intercept of approximately 21. And if we want to maybe think about what is the equilibrium of this system, then it might be useful to factor it and try and identify what are the zeros of this equation. And that's how it's expressed over here. Questions before I go back into our worksheet? Okay, great. So yeah, so just to catch us up, so we had a formula that was about dc dt was, this was our kind of first model, which we then could express by pulling out this constant and write it as minus 0.3 times the quantity of C minus 70. And this is exactly a special case of what is called Newton's law of heating and cooling. And so what this law says is that the rate at which something heats or cools is proportional to the difference between the temperature of that object and the ambient temperature in the room. So this A denotes ambient temperature. The reading materials, if you're looking at like the applications reading in chapter 4, let me just say that they denote that constant as T with a subscript of M to denote the temperature of the medium, which would be the room temperature. I felt like there were enough T's in this formula. We have a capital T and a lowercase t. I didn't want to put another T in this formula. So A is actually more oftentimes used instead of that. But what's important here is to note that this and this are constants. Okay, they're not arbitrary constants, they're constants. Like A is going to be what is the ambient temperature of the room, and K is going to depend on properties of the object. Like that's going to be some property of the coffee cup. And so T is the temperature, capital T is the temperature, lowercase t is time. So let's take a look at this model that we have here, and then we can think about this in general. But I hope that the differential equation, this does not seem like this mystic formula that I have no idea where this comes from. Hopefully it makes sense. Really all we're saying here is that when an object's temperature is really close to the temperature of the room, it's not going to change its temperature very much. But when this difference is large, when the object has a temperature which is much cooler or much hotter than the ambient temperature, then that object is going to change temperature more rapidly, right? So the bigger the difference is between the temperature of the object and the room, the faster that object cools or heats, depending on the situation. So if we are taking a look at this differential equation, dc dt is minus 0.3 t minus 70. In this case, right, we've got, that would be our K, and that is our ambient temperature. So that 70 in that formula, which just might have seemed like a fairly random number, is actually something very physical here. That's telling us that the ambient temperature of the room where we're placing this coffee cup seems to be 70 degrees. But just to review a couple of concepts, remember we have an equilibrium solution. These are constant solutions. And if a solution is constant, that means these are going to be solutions whose derivative is always 0. So to find equilibrium, we set the differential equation equal to 0, and we solve. Sorry, I should have consistent variables here. So if we're thinking about the coffee cup example, then we can see we have one equilibrium solution, which is C is equal to 70. And what this means is that if you took a coffee cup whose temperature was 70 degrees and you put it in a room which is 70 degrees, that temperature of that coffee is going to never change, right? It would remain constant at 70 degrees. And now we're not talking about populations, so we certainly could consider positive numbers and negative numbers. So if we start with a temperature of 70 degrees, we just said, right, this is an equilibrium solution. But right, this equation is autonomous since it doesn't depend on time, so we can set up a phase line and then think about the stability of this equilibrium. So if I plug in a value bigger than 70, what you should see is that the derivative is going to be less than 0. And if I plug in a value, an initial temperature, if the coffee is like 60 degrees, then it would actually warm up and approach the temperature of the room. So we get that this is a stable equilibrium, that no matter what, how hot or cold that object is, if you place it in a room whose temperature is constant, eventually, maybe a long time, that object's temperature is going to approach the temperature of the room. Okay, so this A, this ambient temperature, is actually representing like an equilibrium solution. And with heating and cooling problems, the equilibrium is should be stable equilibrium. So if you were just simply asked, you know, you have this model over here at time 0, your cup of coffee is 160 degrees. How hot is the, you know, coffee cup going to get as time goes off to infinity? We could just look at this equation and say that as t goes to infinity, no matter what the initial value of the coffee is, it is going to approach, in this case, 70 degrees Fahrenheit. So that value for A is really important. Just like we had, you know, it was important to identify the value for L in the logistic models. Here, our equilibrium is the ambient temperature. Okay, any questions? Okay, so there are 2 practice problems that I would like us to work on then for a little bit, and then we can come back and compare our answers. So one of them is an application to economics. I know we have some students that are majoring in econ or doing a double econ math major. And the other one is an application to forensic science. And so the idea here, although neither one of these is technically a cup of coffee that's cooling in a room, the laws that govern the behavior of these variables are the same as the heating and cooling. I'm sorry, this forensic science one is exactly a heating and cooling problem. This one is a little bit different. So maybe let's start with question number 7. And I'm going to break you guys up into some groups to start with that one. And then if you finish that one, you can go back and take a look at question 6. What you would need to do here is set up and solve a differential equation. And so for heating and cooling problems, it's always going to be the same. These would be our initial setup, and the idea is we would want to figure out what A and K are. So in this example, what would our value for A be?
68 degrees.
Yeah, that's right. So that A comes from the temperature of the room. And let me just say that if you change it so that A is not constant, that A is also changing with time, it doesn't complicate it actually too much more. It just makes solving it a little bit trickier, but it doesn't change the model all that much. Yeah, so we've got A is 68 degrees, so we can plug that in. We don't know what K is at this point, but let me just say we've got 2 bits of information, being that we know what the temperature of the body is at 9 a.m., and then we know what the temperature of the body is 1 hour later at 10 a.m. So one of these bits of information should be useful for finding the arbitrary constant in our general solution. The other point is going to be useful to help us figure out what K is. So I'll just say when you're solving in B, leave the constant K in your solution at first. And so when you find the general solution in step B, your answer should have a K in it, and your answer should have some general constant that we get from general solutions. And then you're going to want to use this given information to figure out what those two values are. So I'll leave it there, and you'll have some students, some classmates to talk with to try and work through this problem. There is a feature in the breakout rooms where you guys can ask me a question, since it's hard for me to kind of go through all around. So if you do have any questions, you can send me a message. It'll come to me and I'll know to pop into your room. Otherwise, I'll just be periodically moving around to see if there are any questions. But any questions before I leave you all with your groups? Okay, then let me set up some rooms. Okay, and there you go. So good luck, and I'll be just checking in on your progress. Welcome back, everyone. So yeah, I didn't get a chance to check in with everyone, but I did, at least for those that requested. So based on kind of talking with some of the groups, I don't think the issue was setting up or solving like the general solution for the differential equation, which is great. It was mostly figuring out how can I use the initial values and such to figure out what the constants are. But let me just kind of say one subtle thing here, and that is, okay, this is a separable differential equation. It also is a linear differential equation. If you wanted to do it that way, you could use integrating factors. I think most people thought about it as separating it and then solving. So when you want to solve for this, there is this issue that you do have these absolute values. And when we are solving, we use this. We oftentimes will just say something like this. We just kind of use the letter C to denote the arbitrary constant. And we get a little bit lazy just saying, okay, it's a different C than what we had over here, but it's just some arbitrary thing. So we can call it C. So that's one thing that you may be seeing when you're reading. And if that's giving you any confusion, it's just saying we're multiplying this by an arbitrary number. And the second thing is, well, why does the absolute value seem to not matter? Well, we could define absolute values as piecewise functions. And if t is bigger than 68 or greater than or equal to 68, then the thing inside the absolute value is positive, right? And we would just get this. If t is less than 68 degrees, then we change the sign. And so regardless of whether t is above 68 or less than 68 degrees, we really don't need to worry about the absolute value, because whether I call this arbitrary constant c or whether I call it minus c, that sign is going to get absorbed into the constant c. So we're just as safe saying that this is going to equal this, and depending on what our initial condition is, depending on what the initial value for T is, that's going to determine whether C is positive or negative. So it's not that, you know, we don't care about the absolute value. It's just that the implications of that are absorbed in the arbitrary constant. So the general solution becomes something that looks like this. And right, since all of these models are pretty much the same, all of the general solutions are going to pretty much look like this. This 68 came from the value for the ambient temperature A. And then the groups that I talked with all made a nice decision that we're going to measure time in terms of, let's say, hours from 9 a.m. And what makes that particularly nice is that this then becomes the corresponding value of capital T when lowercase t is 0, if we make t 0 at 9 a.m. And that gives a constant of 22.3 e to the minus kt plus 68. So using the initial condition, we solve for that arbitrary constant C. And then we can use the fact that 1 hour later, the temperature was 89 degrees Fahrenheit. Right, and plug in 1 for lowercase t, plug in 89 for the temperature for capital T, and you can use that to solve for K. And I got approximately 0.06. It's possible that if you measure time in minutes, if your group determined that, then you might get something a little bit different here. But in the end, our model should predict the same thing. Does anybody use time being measured in minutes from 9 a.m.? Okay, and what did you get for, if you're kind of, I think I have that someplace. What did you get for your value for K, Kyle, if you've got that handy?
For K, I got 1.001 times 10 to the negative 3.
Okay. Let's see. Sorry, there's another. Okay. Yeah, we can kind of see if this is consistent. For those that used T is in hours, did you get 0.0? I saw a thumbs up. Is that consistent with what you guys got? Yep. Okay, so then the model for the temperature, we can then plug in our value for K, and now we no longer have any unknowns. So this would be the unique solution to that differential equation. And then this problem was asking us to find the approximate time of death. And the assumption for that could be that the person had kind of the average healthy body temperature at that time. And now it becomes an algebra problem to solve for T. And you should get a negative value because this should have happened before 9 a.m. So when I solved this, I got that T was about minus 5.27 hours since 9 a.m. So that means a little bit more than 5 hours before 9 a.m. So if you kind of do the math, subtract 5 hours and about another quarter of an hour, that puts you at about 3:44 a.m. Any questions about that? Do groups have any questions about any steps in there?
Wait, sorry, can you clarify how you got 22.3?
Yeah, so at this stage over here, or maybe at this stage over here, I should say, we kind of have our general solution. And so now if you plug in 0 over here, and you plug in at time 0, it was 90.3 over here, then you could solve for capital C. So that equation would look like 90.3. I think that was the time at 9 a.m. is equal to C times E to the minus K times 0 plus 68. So that would be the equation you would want to solve.
Awesome, thank you.
Yep. And yeah, so that basically C winds up being 90.3 minus 68.
For this part of the problem, is
Yeah.
it necessary to choose time 9 a.m. as time 0 because the 0 cancels out the K and the what E is raised to? If we chose 9 a.m. to be 1 hour and then the hour after that to be 2, would that be a problem? Do we have to use?
It just makes the algebra more difficult, but you would get the same answer regardless. Yeah.
Okay.
It would just really what we're solving here is a system of 2 equations with 2 unknowns. And when one of those unknowns happens to be at time 0, that's right, the exponential thing kind of is much easier to deal with. And so that's kind of the advantage of setting our base time at 9 a.m. Any other questions?
Yeah, because we know 89 and 90.3, so the time is 1 hour. So can we get the K as the first? Use the dt over dt.
Could you find K first? Was that the question?
Yeah, because can we use the 89 and 90.3 because the time is 1 hour. So we can first calculate the dt over dt, then calculate the k value.
Be careful. I see what you're saying, and that's not a bad suggestion. I think the idea is the fact that we know the temperature at time 0 was 90.3, and we know 1 hour later the temperature is 89, then we can say when delta t is 1, delta capital T was this, and you can approximate the derivative and then use your approximation for the derivative to find out what K is. And I'll just say that it's an estimate, so you won't get exactly the same result. You'll get something that's probably really close. But the reason why it's not as accurate, it's because dc dt is technically how much does the output change when we change the input by an infinitely small amount. And so when you're using a change in time of 1 hour, you know, that's pretty small, but it's not infinitely small. So there might be a little bit of error in there. But not a bad idea at all. That certainly is a good idea. Okay, so let me just, before we end things for today, I'll put the solution to this one up online since we didn't have time to get to this. But it's a very similar sort of model here. And so this one deals with supply and demand. So I'll just say that if you're not interested in applications to economics, then you don't necessarily need to worry about this. If you're not familiar with supply and demand, don't worry about it. But if you've taken a bunch of econ classes, I think this might be of interest to you. So I'll put the solution to this one up online. But you don't have one like this on homework. This is just for some practice. On homework, you have one similar to what we did with question 7. So the homework is up. I will get a reading quiz up for Monday's class sometime either later today or tomorrow. But in the meantime, feel free to get started on the homework. There'll be the first couple of questions you should be able to work on now. And then you'll see a bunch of second order differential equations on the homework assignment that you probably won't be able to solve. We'll talk about that on Monday and Wednesday next week. Okay, thanks everybody. Have a good afternoon. And if you have any questions, feel free to stick around.
Thank you.
Yep.